Good morning, dear colleagues. I'm glad to take part in the conference. I hope you and your family are doing well. My name is Yurii Kyrylenko. I'm a PhD student and researcher in Emergency Preparedness and Radiation Monitoring Department of the State Scientific Center and Technical Center for Nuclear and Radiation Safety. In the presentation, I would like to put our attention on the actual developments in area of source term model for the events with radioactive liquid spills. I'm going to highlight the joint work between the developed source term model and decision support system. So today, in work practice, we can see that more and more often, in order to model the radiological impact on the public, personnel, and environmental, decision support system for nuclear emergency are common used. For example, it's RODOS, Argos, Hotspot, or Rascal systems. In addition to the primary task of the software, they are often applied in frame of emergency preparedness and planning, quantitative and qualitative analysis of possible scenarios taking into account the evolution and phenomenological stages of the events. This is primarily due to the wide range of data assessment tools, both in terms of design capacity and in terms of simplicity of input in and analysis of the results. However, at present, a significant challenge for users of this software is to prepare a correct and complete package of initial data, in particular source term data for each of the emergency scenarios under consideration. For instance, developers of Rascal code have been overcome the obstacle related to fast source term assessment and simplified atmospheric dispersion modeling that is fully justified by emergency response goals. However, the wide variety of potential emergency processes at nuclear power plants does not allow to create a unified tool for preparing source term data that would cover all possible states of the affected facility. In our study, we have the aim to complete the all stages of radiological consequences analysis for the group of events related to radioactive material spills using developed source term models taking into account requirements from side of actual decision support systems. It can be achieved due to solving of the task presented in this slide. Liquid radioactive material, liquid solution which include impurities of radioactive elements, possibly bound in high molecular complexes. The isotopic composition of alaram is determined primarily by the source of radioactive impurities. The main sources of alaram at nuclear power plants and nuclear complexes are as follows. There are primary coolant that is discharged for operational reasons, water that is used to backflush filters and ion exchangers, flow drains that collect water that has leaked from the active liquid systems, and fluids from the decontamination of the plants and fuel fluids. Leaks of secondary coolant, laundries and changing room showers, chemistry laboratories, etc. By the way, on this slide, you can see the consequences of the event with spill of used decontamination solution at Ignalina NPP and in 2010. As an example, issue is a significant problem for radiotherapy medical hospitals. The problem is to analyze the potential events related to the special reservoir system in the underground areas of hospital. On the screen, you can see decay tank systems containing technetium 99 metastable and iodine 31, etc. Worldwide, there have been more than 30 significant accidents with spills of liquid radioactive materials at nuclear facilities for the last 60 years. Among them is the accident at research reactors, nuclear power plants, nuclear complexes, uranium facilities, pilot plants, and chemical plants. Many special computer codes and methods are currently developed to assess with sufficient accuracy parameters of releases for various accidents at nuclear facilities. For example, severe accident code Molitor, developed by United States regulatory body. But according to previous studies, Molitor code has some disadvantages and often require a large amount of input data and calculation time to provide comprehensive assessment. In the world practice of liquid radioactive material related events analysis assessments of the radionuclides distribution in the liquid vapor system are based on the results of research, modeling, and experimental data. In context of normal operation summarized in the standards and guidelines of the US NRC. On the slide, you can see that American national standards and CIS have information on radioactive system for normal operation of light water reactors. So we propose system model of LRAM spills. The proposed approach is based on the theory of non-stationary heat and mass transfer in surface evaporation of liquid heated below the boiling temperature. To solve the problem of unsteady LRM evaporation, four balanced differential equations were written to relate the main parameters of LRM and airspace over time. As outlet from this model, as results, we can provide curves for the air activity in the area and total release in the atmosphere. You can see how the texture works. On this slide, you can see the air activity in the affected area, and you can see the release into the atmosphere. This calculation were provided for the set of different initial data. One of the tasks for the preparation of initial data and boundary conditions for the model is a preliminary ventilation task solving within the established technological parameters. Using such software like ANSYS, OpenFOAM, or SolidWorks software, the influence of the ventilation system flow in the velocity of the underlying inlet air layer was investigated. Some cases are shown on this slide, and also for different inputs. So, developed model of system can be integrated with different tools for those assessment for personal, for public, and environmental. Also, it can be used in case of atmospheric dispersion modeling. You can see some methods or tools. You can see the RODOS system with ring-puff model, Argos system with complex terrain dispersion model, dose projection model from Argos, sophisticated models for short range, CFD-less modeling, simplified Gaussian approach, NRC's max code for probabilistic analysis, Rascal code, hotspot, generous RAD, and etc. From the RAM family codes. Also in this table, I mentioned that the two parameters, array of air concentration in emergency room and array of time integrated activity related into the atmosphere is two important results of working our model. So in Ukraine is commonly used hotspot interrupt and RODOS system. In our calculation toolkit, we have three codes that cover different ranges and contain different atmospheric dispersion models. These are used in emergency center of Ukraine. RODOS system has a different database and different models to provide a comprehensive assessment. We use special numerical weather data to provide our calculation. And on this slide, you can see a general view on source term window in RODOS system. Those assessment is provided according to database integrated in PostgreSQL database of RODOS system. On this slide, you can see some example of radiological assessment. This is dispersion modeling results for event with spill of liquid radioactive materials provided in a LASET model in RODOS system. And also dose projection was done using FDMT model of RODOS system. 1 year effective dose from all exposure pathways except ingestion. This is one of criteria in Ukrainian regulations. So in conclusion, to sum up, for the first time system model for radioactive liquid spills taking into account technological premises and adjacent environmental has been proposed and developed. This model, unlike other models, take into account the parameters of the radioactive liquid composition and design conditions of their storage. Possible ways of software integration of the development a mathematical model into atmospheric dispersion modeling and dose projection toolkit, taking into account the requirements of the adjacent radiological impact assessment tool and the specificity of a liquid radioactive accident spills. The developed model can be applied as useful tool of system preparation in case of LRAM spill in advance as well as in the real time with a reasonable degree of conservatism. It allows to provide an adequate assessment of the radiological consequences for the set of initial conditions of accidents with use of LRAM in areas with forced ventilation. So thank you for your attention.